B9. Right. So B9 talks about argon. And so first question is, right, list 4 ions that are isoelectronic, right? And so as I had mentioned in one of the previous parts, an isoelectronic just means that it has the exact same electronic configuration. But now what we're looking at are ions that are isoelectronic with argon, right, that have noble gas configurations. And so, right, there's a ton of possibilities, right, based off the periodic table. I just gave on the answer key 4 that are the closest and easiest to work with, right? And so if we're looking at the periodic table, right, we have argon, right? We have argon right here. So that means, right, chlorine, -1, sulfur 2 minus are going to be some of them, right? So chlorine minus, sulfur 2 minus, right? Both of those have argon electronic configurations, right? We can move in the other direction. We can say, potassium plus and calcium 2 plus as well. Right. So all of those have the same electronic configuration as argon does. Next part, right, arrange ions in order of increasing size. And so, right, when we're talking about, atomic radius and ionic radius, what we're talking about in those cases is how big the essentially the clouds of electrons around the nucleus is, right? Because the protons and neutrons, right, the nucleus, right, they're really small. It's really tightly packed together, right? That makes up almost zero amount of the actual atomic radius, right? The atomic radius is primarily where the electrons actually reside in those cases. And so the thing that we can think about is if you're adding more electrons to an atom to form an anion, the more electrons you add, right, you're starting to decrease the Z effective that all of the electrons in the valence shell feel. And so because they're now all being pulled less by the nucleus, that means that they can go further out, right? So the radius increases, because you have, not only more electrons that are in there, right, but each one of those electrons now is actually feeling less of the nucleus because now it has to get distributed across more electrons at that valence shell. And so the more negative, something is, right, you would expect it to have a larger radius in comparison. And so looking at that, right, what we would expect then is that the sulfur 2 minus to have the largest radius in this instance. Right, so sulfur 2 minus would have the largest radius, right? We would expect chlorine to then have, the next one, right? Because now that has a 1 minus charge. So we would expect that to increase as well a little bit in that case, right? And then, on the flip side, right, if something is positively charged, right, if you're forming a cation, because you're removing an electron out of the system, but you're not changing the number of protons, all the remaining electrons now that you have are all feeling, the interaction with more protons, right? So those all are now essentially being pulled in tighter because now there's less electrons for that, that nucleus to have to pull in. And so because of that, right, you're getting a shrinkage, right? Because, there's more Z effective that each one of those electrons is feeling. So it's coming in closer together. Right. And so that's why, the trend continues, right? Where now potassium plus would have a higher or a larger ionic radius compared to, calcium plus in those cases. Because, right, the Z effective is going to now be higher on those ions comparatively, right? Because now they're feeling much more of the nucleus because there's less electrons for it all to get distributed on. And so even though, right, all 4 of those have the exact same electronic configuration, because they all have different amounts of protons, right, that's going to then change how big the overall radius of that ion actually is in those cases. So part C, would you expect these isoelectronic species to have similar chemical or physical properties? Why or why not? No, we would not, right? Because they all have different charges, right? So they're all going to be interacting differently with other charged species, right? So if you have something that has a 2 minus charge, right, that's a very localized amount of negative charge. That's going to want to interact much more strongly with positive charges compared to something that only has a single negative charge. Same thing with positive charges, right? Positive charges aren't going to want to interact with other positive charges, and they're going to want to interact with other negative charges. And the more positive charge you have, right, the more negative charges it's going to want to interact with. So you have that as a feature, right? In terms of physical properties, right? We already talked about one physical property, size, right? Those aren't the same, right? We already know that the size of the ions are going to be different, even though they have the same number of electrons in those cases, and that goes back to the nucleus and stuff, and so it relates to that, right? Same thing with ionization energies. Thinking about the transition of S2 minus, right? If you were to do, try to convert that back down to S minus, that's going to be a very different ionization energy, right? To take out, that extra electron compared to like calcium 2 plus, in those cases, right? All of those are all going to have different ones because the number of protons is different between all of them. So the Z effective is different for all of them. And so that's what, is impacting all of that.